next presentation, we have Jiajun from Ryzen. Jiajun is a senior product manager at Ryzen Energy. He is going to talk about scaling up cost-optimized HJT production. Ryzen is also a very old company that has been working on heterojunction technology. So Jiajun, the floor is yours.
Hello, everyone. Let me share screen first. Oh, can you see the screen now? Just load it up.
Yes.
Okay, so hello everyone. I'm Jiajun here, Senior Product Manager of Ryzen Energy, and happy to here and present you and share the updated technology of Ryzen Energy. As we know that Ryzen has been in PV industrial for many years and have grown with it. We entered in PV industrial since 2002 and become Bloomberg top 10 manufacturer since 2015. And we are also pioneer in the heterojunction production. By 2019, we already launched our first heterojunction model, which is called Ziga series, has power output from like 335 to 355. And by 2019, we have upgraded our heterojunction production based on the big wafer and launched our Hyper-ion series, has power output up to 700 watts. And also you can see on the roadmap showing some progress on our productions. By February 2022, we have already equipment for the first production line in Bonn in the factories. And by February, our first production was on operation and reaching average efficiency around 25.3% and a maximum up to 25.6%. And by June, the max efficiency was put in the full run and started to deliver to all the world. And why Ryzen firmly chose heterojunction technology as our key technology? Because we have studied all the PV model technologies. And from nowadays mainstream PERC, which has reaching his bottleneck 24.5%, is known to all. And the emerging N-type technology, TOPCon, also heterojunction, with efficiency potential up to 28.5%. And which is also next generation technology tandem cell, which can combine the PERC together with heterojunction, TOPCon, or other technology, which has potential up to 45% or even higher. And by comparing this old technology, we found out heterojunction is a product with the greatest potential to realize our target, which is lowering the LCOE and also the carbon emission, because heterojunction has a higher power output and high efficiency and higher battery factor and a better temperature coefficient and low degradation, which helped us to obtain a higher generation yield. And because the geometric structure and the low temperature production production procedures, we can reduce also a lot, the carbon emission. Along with thinning of the silicon wafer, we can also reduce a lot of raw material consumption. And to realize the industrialization of heterojunction mass production, we also, of course, during our R&D, we've been facing a lot of challenges. One of the big challenges is to reduce the cost while increasing the efficiency. By comparing all other 8 aspects in this diagram in the left, you can see that in terms of carbon emission, scalability, equipment and compatibility, and bifacial factor, and the cell efficiency, also the wafer cost, we are better compared to other two technologies, TOPCon and PERC. And the only weakness we're facing now is the equipment cost. Because you know that for heterojunction, we have to invest in brand new equipment. But I think this can be analyzed when we are reaching whole industrial scaling up and ramping up. And for the non-silicon cost, we know that to have a better contact, and we have to use the low temperature silicon paster for the heterojunction and ITO as TCO layer, which is higher compared to the PERC and the TOPCon. So to overcome all these challenges, we first look into the cost structure of a heterojunction solar cell. As you can see, silicon wafer and silver dominates the cost structure over like 75%. So maybe we are choosing the measure we adopt to reduce the cost and reaching the industrialization. We were focusing on these two aspects first. And as the silicon wafer has like a 55% share of the cost structure, so the first thing we're thinking is to thinning the wafer thickness. During our R&D, we have we already reduced our thickness of our wafer from 150 to 100 micrometer. Maybe there's wonder that, or doubt on that, by thinning the wafer, if there's some affecting on the efficiencies or reliability of the solar cells and wafers. And through our studies, which verify from these pictures, we can see that for left, you see the relationship between the wafer thickness of the optical observation. And we can see in the wavelengths less than 700 micrometer, the absorption rate were basically the same. The only difference what happens when the light wavelengths reaching the infrared regions. And by reducing the wafer, maybe the absorption will be slightly lowered. But compare the line here, which is blue, stands for the 110 micrometer, and which is orange stands for 160 micrometer. The difference between these two lines is very narrow. So we're thinking that by decreasing the thickness wafer from 115 to 100, will be no big impact on the efficiencies of the solar cells, and also on the observation of the lights. And on the fourth diagram in the left, first one shows the difference between the relationship between the ISC with wafer thickness with the thinning of the wafer. We're seeing that the ISC was slightly decreased, but in contrast with the thinning of the wafer, the VOC increased a little bit. So to come to these two factors together, we'll see the two pictures in the bottom left, seeing that the relationship between the fill factor with the thickness and the relationship with efficiency with the wafer thickness. By thickness wafer reduction, we're seeing that the efficiency and fill factor increase a little bit first and decrease slightly when reaching 100 micrometer. And by the observation and the studies, we found out by slightly decreasing from 130 to 100 micrometer wafer, the efficiency and wafer fill factor will be no big difference will be no big change. So we believe that efficiency will not be compromised when we're thinning the wafer to 100 micrometer or even slightly lower. And the other aspect is also, which also Christian also mentioned, by maybe in common sense, maybe people think by the thinning of the wafer, the flexibility the wafer will be more fragile compared to the conventional one. But by testing, we're seeing that we've compared the 105 micrometer PERC cells and 130 micrometer TOPCon cells and 90 micrometer heterojunction cells. It seems that for the PERC one, it will be cracked when the deformation reaching 46 micrometer, and for TOPCon, it will crack by the 53 micrometer. But for the heterojunction, even it's reaching the maximum load test, still remain intact, which verifies the reliability of a thinning or thinner with ultra thin wafer for the heterojunction. And this is some data we have been extorted from the factory. From April to August, we're seeing the yield of the wafer production is increasing rapidly. By the end of October, it has reaching 99.2%, and fragmentation rate has reduced from 20% to 0.2%. Aside from the thinning of the wafer, we also lowering the silver consumption by adopting the low silver content paste for paster. And in the right, it shows some SEM cross-section pictures of the low content silver paster. As you can see, for this silver content, two material was being adopted. In the middle, within there we have seen a share which is silver share, and in the share is like a copper, which is low cost like a material. We think the share is have like 90 around 80 to 100 micrometer thickness, and with this local we reduce a lot the silver consumption, because basically only 50% of the silver. We reduced 100% silver content to like 50% as for now, and thus we have reduced the metallization cost to like 1.02 cents per watt, basically the same level to TOPCon. And we believe that by the further study and R&D, we will reduce our like silver consumption up lower to 0.64 by next year, reaching the same scale for the compared to the TOPCon. And also there are some worries when we are doping like low silver content paste, because there's other material within this paste, like such for copper things. But we have done some tests to verify there will be no big effect. First thing that we have to done some SPX test to verify there's no like vertical or no like horizontal diffusion of low cost materials in the silver paste. As you can see, we selected like a point between 2 fingers and a middle point of 2 fingers and 400 micrometer diameter circles. We like tested if there's some like penetration or diffusion of the other element within the low within the pasters. As a test, we can see we only like indium, oxygen, carbon, and tin and silicon or chromium was detected, but no copper was detected. So it verifies there's no like diffusion in the horizontal direction in the pasters. And in other aspect, we also tested the like vertical diffusion of the like low cost metals, which is copper. And we selected a few points in depth under the like fingers. And as you can see, we have a 4-step, 4-point selected. And within all the 4 trends from this 4 picture, we can see only silicon was detected, no copper was detected, which verifies that we don't see any copper diffusion in the like vertical direction in solar cells. And also, if after longer times of like elimination or like energization, if some breakage of the like silver share, we will still have the worry that maybe the copper will like penetrate in the silicon structure, causing some like degradation of the efficiency. And this test will solve that. We test the like reliability when this happens. As we know, for the heterojunction, we are using the ITU as the like TCO layer, and the silver paste that was being printed on this surface. So we tested this structure. As we can see, there's a sample structure we have created with like silicon on the bottom and 10 micrometer ITO on the surface. And on the surface, we're using like copper plating as instead of like low silver pasted, because this is like pure copper, which may be like this is more like a stringent test compared to the low silver pasted. And under such case, we verify that under only when the annealing temperature reaching like over 650 degrees, then the sheet resistance of the solar cell structure will rapidly increase. And as we know that for the heterojunction production, we also like procedure was conducted under low temperature, which is lower than 200 degrees. So there's no risk that we will reaching this high annealing temperature. There's no risk of like a rapid change in the like sheet resistance after long time for like performance or long time use of these models. And even if there's some like breakage of the like silver share of the like low silver content pasters, we have like for silicon for our heterojunction models, we are adopting like 80 micrometers ITO. So this is like a very good barrier for the copper element. So this is also verified that we don't have such rate. And with all and we also tested compared the like a pure silver like paste with our low silver paste heterojunction for the heterojunction from October and to in the October last year. and verifies that the like power generation between the pure silver silicon heterojunction cell and low silver content heterojunction cell are basically the same, no big difference. And thus, we're thinking this is the right way to reduce like a cost for the heterojunction mass production, and also while maintaining the like efficiency. And in the next step, we will like further reduce the cost for the like silver consumption, reduce the silver content lower than 45% in this Q4, and next year we'll be reducing further to like 40% or lower. Thus, the silver consumption will be reduced from 9 micrometer to like 8-7 in next years. And all the way along, we also accelerated the screen painting speed for the for the heterojunction cells, which is the kind of ramping up of like heterojunction mass productions. And also to verify the reliability, well, after doping our like thinning wafer and low content silver paste, we done all kind of tests like a mechanic test, dynamic like TC circle, thermal circle test, like dump heat test, and like humidity freezing test, and hotspot test, and UV, and also the which concerning a lot by the others, which is UV test. After test, we found out the reliability and the performance of the models are still remain within the IEC standard. So it's feasible to adopt all the technologies. Of course, we have also adopting other technology like zero bus bar, and we're also introducing light conversion fuels in the next step. So there's a further potential to increase our efficiencies. And thus, based on all this advancements, we have established 2 new facilities this year for heterojunction, one in Nanbing and one in Jintan. And in total, this is 15 gigawatt. And for these 2 new facilities, it's we build a smart factories. All will be fully automatic, and the transportation between different kind of sectors will be all run by automatic guided vehicles, delivering all kind of materials to avoid some manual faults. And in next year, we will still planning new facility to increase our production capacity up to 21 gigawatt, which is 60 gigawatt more. And this is some key metrics we have been absorbed from the last October, this October, seeing that for production capacity for the cells, we have reaching 866,000 pieces per day, and the average efficiency has reaching 25.42, and the yield rates of solar cell structure have reaching 99.24, and the mass production of for the cells has the fragmentation rate has lower than 0.7%. And this is some optical patch from our mass production recently. And from this distribution, you can see the average efficiency we have reaching 25.8%, which is 0.5% by 2 years ago, higher compared to half years ago. And however, reduce our wafer solar cell thickness to 9 nanometer after etching. And the champion efficiency we have reaching the 26.1%, and our target for the next year is to reaching the average efficiency 26%. And overall, to summarize, we have during the long time of research and studies, we have risen as pioneer of heterojunction manufacturer. We have reaching 4 firsts among all the heterojunction manufacturer. We are the first one has mass production of the zero busbar solar cell, and we are the first one to reduce the solar cell thickness to 90 micrometer, and the first one to reduce the silver consumption lower than 9 micrometer per watt. And we also adopt our own patent hyperlinked zero busbar technology for the intercell connections to reduce a lot to increase the reliability of solar cell structure. And thus we have this our main our champion product for heterojunction. As you can see, our key power output for next year we're reaching over 700 watt. Again, for the second half years, key power output will reaching from 705 to 715. And this is some updated data we have obtained for the last 2 months in August and September. As you can see, the power generation compared to PERC, we have like 4 to 6%. This is from the practical side. And from the simulation, we also see the difference. We have selected 25 locations over the world with typical climate conditions. It verifies that our practical sites result is saying that compared to the PERC, we have around 4.5 to 6.5 power generation gain within the life cycle, and compared to TOPCon, we have 1.3 to 3.5% higher power generation yield. And to summarize, we will think that hadron product for Ryzen is with a great potential to reduce LCOE and BUS, and also we have reaching the gigawatt scale, so we are ready for the utility scale project supply and have already delivered more than 500 megawatt over the world in this year. And in next year, this will be ramping up rapidly, I think, to gigawatt scale. So we need to see. That's it. Thank you.
Okay. Thank you very much for this presentation. I have one quick question. So when you were saying that the silicon cost is the major contributor and you were able to reduce the thickness of the silicon wafer to 90 microns. So do you also get benefited equally when you are reducing the wafer? Is it not that after a certain time, it's more difficult to manufacture such a thin wafers, or you are directly transforming those advantages in the cost?
This is a compensation method. I will say that you know that now the silicon cost now is dropping rapidly from the previous time to now, but since the technology we have reaching the mass production of the technology, so the cutting cost of this thinner wafer is slightly higher compared to conventional one, but it's still within our tolerance. We're thinking this is slightly lower compared to the cutting cost, the silicon cost compared to the PERC and also the TOPCon ones.
And as Christoph mentioned in his keynote, so what about the TCO? So are you worried about indium right now? So do you also have any plans of reducing indium content or getting away with indium? Can you say?
We'll say that for now, we also have our R&D team is also studying some indium frame TCO materials. But we'll see in short term, this is not ready for the mass production. Maybe next 2-3 years, with some new technology was being to made, then we will be changed to a indium frame, because we believe that heterojunction products has to be eco-friendly to reduce not only reducing the carbon emission, which is, as Christian also mentioned, we have lower 400 kilowatt kilowatt equivalent carbon dioxide emissions per kilowatt peak. We also need to no pollution to the environment, which has to be indium free. We are focusing on that also.
Okay, thanks a lot for the presentation. So please stay tuned and enjoy our conference while also answering some questions. I think they're popping up just now as I see.
Yeah, no problem. Thank you.
Thank you.